A cantilever beam of rectangular cross section is subjected to a load W at its free end. If the depth of the beam is doubled and the load is halved, then deflection of the free end as compared to the original deflection will be. Here, when a cantilever beam is subjected to a concentrated load at the free end, then the deflection at the free end is given by WLQ by 3A. So here it is directly proportional to load and inversely proportional to moment of inertia. Again here moment of inertia is nothing but BdQ by 12, so that the moment of inertia is directly proportional to BdQ. Again here it is here the depth only the depth varies, so that it is directly proportional to W by dq. So here the load is doubled, sorry, depth of the beam is doubled and load is halved. That means here it is W by 2 and D is 2D whole cube, that is 1 by 16 W by d cube. So that after the dimensions changes, that is the depth is doubled and load is halved, it will become, the deflection will become 1 by 16 of the original deflection. So that the right answer is C. Determine the diameter of the solid shaft which will transmit 90 kilowatt at 160 rpm if the shear stress in the shaft is limited to 60 Newton per mm square. Here we know that the power transmitted by shaft is given by 2 pi nt by 60, where n is the rpm of the shaft and t is the torque induced in the shaft. So here T is equal to 60 into, and power is given by 90 kilowatts, that is 90 into 10 cube watts, and here N is 160. So which gives a value of 5371 Newton meter. And we know that the relation between the torque and shear stress induced in the beam is equal to pi by 16 tau d cube. So here where tau is the limited stress in the shaft, limited shear stress in the shaft, and we'll have to find out the diameter of the shaft, that is d. So here d is equal to cube root of 16t by pi into tau. So here all the values are known values, that is 16 into 5371 by pi into tau is 16 Newton per mm square, and here the torque in 5371.5 Newton meter, so that put another 10 cube here, so which gives a value of 77 mm. So in the option, the right option is A. A is the right answer. A journal bearing 60 mm in diameter and 90 mm long run at 450 rpm. The oil used for hydrodynamic lubrication has absolute viscosity of 0.06 kg per meter second. If the diameter clearance is 0.1 mm and Sommerfeld number is 14.3 into 10 power 6, then the safe load on the bearing is. Here the Sommerfeld number is given by S is equal to Zn by P into D by C whole square, where D is the diameter of the journal and C is the diameter clearance and Z is the viscosity of the fluid and N is the RPM, and here P is the safe pressure or the maximum pressure that can be applied on the bearing, and S is the Sommerfeld number. All the values are known values except P. So here we will have to find out the P. Here S is given by 14.3 into 10 power of 6 is equal to Z is 0.06 and N is 450 rpm. We will have to calculate the P, and diameter of the journal bearing is 60 mm and diameter clearance is 0.1. So from this equation you can find out the maximum pressure that can be applied on the bearing, that is 0.68 Newton per mm square. Now the safe load on the bearing is equal to the pressure into surface area, that is LD. So here 0.68 into 90 into 60, which gives a value of 3672 newtons. So in the options, the right option is B. A machine component is subjected to flexural stress which fluctuates between 300 meganewton per meter square and minus 150 meganewton per meter square. Take factor of safety as 2. Find out the value of minimum ultimate strength according to the Soderberg relation. Here, the given member is subjected to flexural stresses, that is, and in the Soderberg equation, it is given that 1 by factor of safety is equal to sigma m by sigma y plus sigma v by sigma e, where sigma m is the mean stress and sigma v is the variable stress, and sigma e and sigma y are endurance strength and yield strength of the material. So, and we know that sigma y is equal to 0.55 times the sigma u, that is the ultimate strength, and sigma e is equal to 0.5 times sigma u, and here sigma m is equal to, that is mean stress, sigma 1 plus sigma 2 by 2. Here sigma 1 is the upper limit and sigma 2 is the lower limit, that is 300 minus 150 by 2, which is equal to 75. And here variable stress is equal to sigma v, that is sigma 1 minus sigma 1 minus sigma 2 by 2, which is equal to 300 plus 150 by 2 is equal to 225 meganewton per meter square. Now substitute these two values in the given equation. Already factor of safety is given that 2, so that here 1 by 2 is equal to 75 by 0.55 sigma u plus 225 by 0.5 sigma u. Now from this equation you can calculate sigma u, that is the ultimate strength, so is equal to 1172 meganewton per meter square. Match list 1 with list 2. Here list 1 consists different dimensionless numbers and list 2 consists the related parameters. Here in list 1 there are the 4 numbers. One is Fourier number, Weber number, Grashof number and Schmidt number. And here list 2 consists surface tension, mass diffusion, natural convection, transient heat conduction. Here Fourier number belongs to the transient heat conduction, so that here P matches with the 4, and Weber number is belongs to surface tension, so that it is 1, and Grashof number belongs to natural convection, so that R relates with 3, and here Schmidt number is relates with mass diffusion, so that it is S2. So